A hash table is an efficient way to map an identifying value with some associated data. We'll call the identifying value a key and the associated data a record. For example, we could map names to addresses. The key would be the name and the record would be the address. Or we could map words to a counter of how many times that word appears in a text. In this case, the key would be the word and the record would be the counter for that word. The advantage of a hash table is that it allows us to quickly look up a record based on a key without having to search through the entire data structure. In this part of the lecture, we'll be discussing an implementation of a hash table called an open addressing hash table. Let's take a look at how an open addressing hash table works. At the heart of a hash table is an array. Let's say that our keys are words that we represent using C character strings. We want to insert a key into our hash table. Consider the example key apple. To determine the location of the key apple and its associated record, we'll use a special function called a hash function. The concept is simple. We give a key as input to the hash function, and it outputs the location in the array where the key and its associated record will be stored. This location is called a bucket. Say we have a hash function called h. H of apple might evaluate to the bucket address 3, and will store the data for our key there. And h of orange might evaluate to bucket 1. This operation of adding new data to our hash table is called an insertion. You may be wondering what happens if two keys have the same hash value, that is, when they map to the same bucket. There are several techniques for resolving these collisions. Let's say that apple is already inserted into bucket 3. Next we want to insert orange, and its hash value also maps to bucket 3. Oops. Of course, that bucket's already taken, but bucket 4 isn't taken, so let's just use that one. Thus, our strategy is if during an insertion the target bucket is taken, then we'll try to insert into the bucket plus 1. This is where the name open addressing comes from. If the address where we want to store our data is already taken, we'll just use a different address. Let's do another example. If Kiwi were to evaluate to bucket 3, that bucket would be occupied, so we'll try bucket 4, then bucket 5. Since bucket 5 is empty, we'll insert Kiwi there. Keep in mind that it's possible that there isn't a free bucket to insert a new record into. An open addressing hash table of size m will only hold m records. This technique of probing adjacent buckets until we find an empty bucket or the key that we're looking for is called linear probing. Although it's simple, it suffers from a problem called primary clustering. Notice how long runs of records build up. If we were to look up a record for a certain key, k, it's no longer sufficient to check only the bucket at h of k. We'll have to check h of k, then h of k plus 1, then h of k plus 2, and so on until we find the key that we're searching for. Or we encounter an empty bucket, or we've checked all the buckets and determined that the key isn't in our hash table. This might be okay. Having to check 1 or 2 buckets on average isn't a problem, but as the hash table fills up, or we're unlucky and we get lots of collisions from our input keys, then the advantage of the hash table is lost, and we might as well be using a regular array. But not all is lost. We can avoid these long runs of records with a different hashing strategy called double hashing. The hash function for a double hashing strategy takes the following form. Where h1 and h2 are two different hash functions, m is the size of the array, and I is the number of buckets we've already probed, starting at I equals 0. But don't be intimidated by the mathiness of this hash function. It's quite easy to use. To do an insertion or a key lookup, we'll initially probe the bucket at h of k, 0, then the bucket at h of k, 1, then h of k, 2, and so on until we find either an empty bucket or the key that we're looking for, or we've probed all the buckets. The double hashing strategy works much better than the linear probing strategy, but we have to make sure that m, the size of the array, and the value of h2 meet certain constraints. M, the size of the array, and the value of h2 must always be co-prime. In other words, the greatest common factor of m and h2 must always be 1. One way to do this is to make sure that m is a power of 2 and that h2 of k comma I always returns an odd value. In the next part of the lesson, we'll go over a sample implementation of a hash table in the C programming language. Until next time.